Dear ladies and gentlemen, I'm honored to present our work on a multimodal Aerial-Tethered robot for tree canopy exploration here at the Agri-Robotics Award session of IROS 2022. I'm Steffen Kirch-Georg and a PhD student at the Environmental Robotics Lab at ETH Zurich. Forests and their biodiversity enable human life on Earth. They provide food and nutrients, act as a source of materials and medicine, purify water and air. They absorb and buffer extreme events and regulate our planet's climate. And with an estimated total economic value of $16 trillion per year, these ecosystem services play a major role to our well-being and wealth. Yet, our relationship with nature is broken, with forests and biodiversity being lost at alarming rates. Agriculture, logging, and livestock farming drive deforestation today, while a changing climate and invasive species will become major threats to our forests in the coming decade. With our wealth and health and well-being depending on forests, it is vital that we learn how to protect and conserve these forests, while being able to sustainably exploit them for our demands. So far, we have not managed to do so, as we lack data from within these ecosystems for a holistic understanding. This is the reason why we are looking at novel robotic data collection methods within forests and their canopies. But how would we collect data in such a remote, difficult-to-access environment? To date, it is mostly labor-intensive work with experienced climbers that can collect data at various heights. In some places, forest towers are constructed and monitoring equipment is deployed. Alternatively, with the canopy crane, a larger area can be monitored. But all in all, these methods are neither scalable nor cost-efficient and sometimes even risky. Therefore, we would like to exploit robotic solutions to access these environments. Drones are increasingly used to monitor forests from above, but due to the dense, massively cluttered, and dynamic environment of forest canopies, drones cannot safely fly within them, requiring a new robotic approach to this problem. Therefore, we propose a novel robot that can be deployed from the top of a tree or directly from a drone, and it combines tethered with aerial locomotion to move within the canopy. While moving within this environment, it can collect vital biodiversity and climate data. Tethers have already been deployed on a variety of robots. Within terrestrial robots, tethers have been exploited for locomotion, navigation, and planning in challenging environments. For example, on Dante-2 or NASA's rovers Axel and T-Rex, as you can see. Conversely, tethers on aerial robots have been used in a very different way. Most commercial applications use tethers for power and communication link, while research is ongoing to use tethers to perch on branches or build structures. However, none of these works really exploit the tether for locomotion purposes. After being deployed either from a drone or the top of the tree, our robot can move with a tether vertically and with two thrusters in 3D through the canopy. With these thrusters, the locomotion modes shown on the right are possible. First, the robot can simply spool and unspool the tether to move vertically with lower noise and power consumption. Second, with both thrusters, it can pitch, and with a differential thrust, it can yaw. Lastly, the robot can combine all three movements to locomote in a conical workspace. Using both tether and thruster actuation, the robot can therefore move around obstacles such as tree branches and foliage, or move towards interesting areas of the canopy. We translated the presented locomotion strategy into this robot design. The robot has two ducted propellers and a servo for tether actuation. Additionally, a flight controller, electronic speed controller, and Raspberry Pi Zero as system on a chip are integrated together with an HD camera for observation purposes. The robot is effectively a double pendulum system and can be described through the tether angle theta, the robot body to tether angle phi, and there's the sum of these angles as the robot pitch angle, as well as the tether length LW. The main design parameter, apart from the weight of the system, are the location of the center of gravity and the center of thrust, or more precisely, their location with respect to each other. The ratio R, LG divided by LT describes the location of center of gravity with respect to the center of thrust. There are three possible configurations. With R smaller than 1, the center of gravity is above the center of thrust. The robot leads in front of the tether as shown. When gravity and thrust act in the same point, the system reduces to a single pendulum with R equal to 1. And the center of gravity below the center of thrust, the robot lags behind the tether for R greater than 1. With a force and moment balance, we can then derive theta and phi as a function of the thrust T, the weight Fg, and the ratio R. Here, we plot the three angles, theta in blue, phi in orange, and their sum, the robot pitch angle in green on the y-axis over the normalized thrust or thrust-to-weight ratio on the x-axis. On the right is a visual representation of the system. As we increase the thrust, the angles experience nearly linear increase before an asymptotic behavior. The robot body to tether angle phi increases sharply, and the tether angle reduces to 0 degrees as the thrust is pointing vertically upwards. We can also vary the center of gravity and thus change the ratio R. At a ratio of 1, the system reduces to a single pendulum behavior with phi equal to 0. Phi turns negative and the robot turns to a more vertical position with R greater than 1. For R below 1, the robot body to tether angle phi is always positive, and the robot body will be more horizontal the further the center of gravity is away from the center of thrust. We validated the model with experimental data for the three shown configurations. The robot pitch, theta plus phi, was acquired from the flight controller, and a rotary encoder was reading out the angle phi from a 3D printed tether joint. The angles are plotted over thrust-to-weight ratio as before. The dotted lines are the model, while the shaded lines are the experimental data. The data shows very good agreement with the model data. Only at high angles, the system starts to oscillate and deviations are divisible. For R equal to 1.18, a thrust-to-weight ratio of roughly 0.7 was only reached as additional mass was added to the robot to shift the center of gravity, and the thrust was not sufficient to go higher on this curve. We teleoperated the robot outdoors in a cluttered tree with a simple PID controller on the robot pitch. On the right, you can see the recorded data of desired and measured robot pitch in blue and orange respectively. In the bottom three graphs, you can see tether speed, integrated tether length, as well as yaw rate. Here, the robot yaws to reorient to be able to overcome the highlighted branch. Overall, the robot is able to follow the desired pitch, but some oscillations occur, especially as the tether length increases. Furthermore, manual yawing was necessary to keep the robot aligned, as we have no closed loop for the yaw angle yet. In case of propeller failure, it is also possible to retract the system using the spooling mechanism. While not ideal as the robot swings back and forth, it allows for emergency retrieval of the system as shown in the video. To conclude, we presented a novel multimodal aerial-tethered robot able to move within a tree canopy from the top down. The tether enables resting, low power consumption, movement, emergency retrieval, as well as increasing safety. The thrusters, on the other hand, allow for 3D movements to avoid obstacles or move to certain areas of the canopy. Our future work will further refine the system with respect to dynamic modeling and control, visual perception for obstacle avoidance, and robotic deployment to the top of a tree with a longer-term goal of autonomous exploration of tree canopies. And here you can see a sneak peek of the next iteration of this robot. With this, I conclude my talk and thank you for your attention, and I will be glad to answer any questions you have.